Welcome to Tomorrow Unveiled, your essential guide and weekly shortcut to being well-informed about the rapid acceleration of the world around us.
Today we are focusing squarely on what happened, not what might happen. We're taking a deep, detailed look into the absolute reality of space operations during a period that often gets overlooked.
Right, that frenetic close of 2025 and the immediate start of 2026.
Exactly, that time right between Christmas Day and New Year's Day.
And that really is the inflection point, isn't it? For nearly a decade, we've all been talking about new space hype, the promise of cheaper, faster access to orbit, all that glorious potential of commercial enterprise. But the data our research team compiled for our analysis on Tomorrow Unveiled, it confirms a definitive transition this week.
A huge one.
The shift to industrial space reality is just not about potential anymore. It's about sheer, brutal, and sometimes messy execution at scale.
Indeed. Our dedicated research team that compiled this information concluded that this transition period, far from being some kind of holiday lull, was defined by a frantic acceleration of mature capabilities.
A frantic acceleration. I like that.
If you were looking for signs that the space economy has, grown up shedding that new space moniker for something far more durable and demanding, this was it. It was the week that formalized the industrialization of the final frontier.
So why should you, our listener, care that this transition happened this particular week?
Well, it's because the foundational pillars of a true space-based economy are locking into place right now.
What do you mean by pillars?
Everything from basic logistics and standardized utilities to highly complex global connectivity and autonomous services. The architecture of the future is being built today, and the speed is just breathtaking.
Breathtaking is the right word.
Exactly. The key themes that were corroborated across all our sources were really threefold, and they describe the mature structure of this new reality. First, a record-breaking operational cadence that solidified the launch market structure, making access to orbit, routine, if intensely competitive.
Right.
Second, major strategic realignment, particularly in the national security sector, which is suddenly prioritizing rapid, resilient access above all else.
And the third?
And third, critical infrastructure breakthroughs in autonomy, connectivity, and on-orbit services that moved ambitious technology from the theoretical drawing board to daily operational reality.
Okay, let me unpack all of that. Let's start with just the sheer scale of operations, because the numbers coming out of 2025 are, frankly, staggering. They confirm the industry is no longer operating like some niche government-run science project.
Not at all.
It's operating like a global logistics network.
The comparison to an airline or a shipping giant is absolutely spot on, especially when you look at the launch statistics globally. What stood out most to the research team wasn't just the total number, but the sustained, near-daily frequency of missions. The cadence achieved in 2025 sets an entirely new baseline for what's considered normal in this industry.
And the dominant player in that logistical shift is, it's unequivocally SpaceX. The company didn't just break its old record. It absolutely shattered it. The data shows they completed an unprecedented 165 orbital flights in 2025.
165.
When you hear that number, 165, it's truly mind-bending.
And when you analyze that frequency, it translates to an average launch rate of one mission every 2.2 days.
Every 2.2 days, wow.
Think about the infrastructure, the workforce, the regulatory bandwidth required to maintain that kind of regularity. This level of rapid, predictable access it was just science fiction a decade ago. It completely normalizes the entire process of deployment.
And that normalization of access, that directly translates into market control, doesn't it? The scale provides some really stark context for their market dominance.
It really does.
This single company accounted for approximately 85% of all American orbital launches in the year. 85%.
Our sources actually term this a monopoly of logistics. It's an incredibly powerful concept.
A monopoly of logistics. Explain that.
It means that whether you're a commercial operator like Amazon, a foreign government with a sensitive payload, or even the U.S. military, if you need to get something into orbit, your schedule is largely determined by the availability and frequency offered by one single provider.
So they set the pace for everyone.
That capability establishes the global tempo. It forces every other competitor to play catch-up.
And that tempo is aggressive, which brings us to the competition. China achieved a national record of 92 orbital launches in 2025. That's a massive logistical achievement. It solidifies their position as the world's clear #2 launch power.
It does.
But I have to ask, Is that 92 launch number really meaningful if they still haven't solved the economic challenge of reusability? Or are they just burning money to keep pace with SpaceX?
That is the essential friction point, and it's why the sheer number alone doesn't tell the full economic story. While China achieved that record, and they did it even as they faced persistent challenges with reusability trials.
Right, the Long March 12A and Zhuke 3 boosters had those landing anomalies.
Exactly. So while they hit that number, the crucial comparison is the cost difference. SpaceX launched nearly twice as many missions as the entire nation of China.
And that difference is the gap created by economics, not just engineering.
Precisely. That's the economic moat, a term used frequently by the analysis team.
The moat.
Right. SpaceX achieved its 500th successful booster landing in 2025 and extended the flight leader's life cycle to a remarkable 32 missions.
32 missions on a single booster.
And that technical accomplishment translates directly into an economic barrier for competitors. The marginal cost of a Falcon 9 launch has been driven so low that it effectively suppresses the capitalization and development of all competitors who can't match that reuse capability.
So without it, you're just constantly fighting against a vastly cheaper alternative.
It becomes a war of attrition. You just can't win.
That aggressive market tempo forces everyone else to think fundamentally differently about their strategy, about their logistics. And nowhere is that pressure cooker more apparent than in the strategic maneuvers we saw this week, namely the Bruno effect.
Ah, yes.
This signals that Blue Origin is taking the competition for high-value national security contracts incredibly seriously.
This was the biggest surprise of the week, for sure. It was announced right after Christmas. Tory Bruno, the highly respected CEO of United Launch Alliance,
Really?
departed ULA to join Blue Origin, taking the reins of its new national security group. This isn't just a personnel change. It's a strategic merger of cultures, and yeah, it sent shockwaves through the defense industry.
Bruno is an industry titan. He's known for his relentless, almost fanatical focus on mission assurance. Under his leadership at ULA, the company maintained a pristine 100% mission success rate.
Gold standard.
Absolutely. It's the gold standard for the Space Force and the NRO, the agencies that launch the most expensive, most sensitive national assets. Why is that specific 100% reliability discipline so vital for Blue Origin right now?
It's crucial because Blue Origin is aggressively competing for the lucrative Phase 3 National Security Space Launch contracts, the NSSL contracts.
Right.
Launching a billion-dollar spy satellite requires more than just raw lift capability. It requires proven, process-oriented, 100% reliability over decades. By bringing Bruno in, Blue Origin is acquiring instant credibility.
And the institutional processes that go with it.
Exactly. It signals that Jeff Bezos is integrating serious old space discipline, the paperwork, the double checks, the conservatism into his new space ambition. It validates Blue Origin as a serious defense and security contractor, ready to challenge Northrop Grumman and SpaceX for the biggest payloads.
And that focus on national security, it goes beyond just their massive launch vehicle, New Glenn. It extends into the orbital infrastructure Blue Origin is developing.
Specifically, their Blue Ring platform.
Right. This is the strategic pivot up the value chain.
Absolutely. The Blue Ring is their answer to the question, what happens after the payload is delivered?
So it's not just a taxi service.
Not at all. It's described as a multi-orbit tug and utility platform designed to service, maneuver, and inspect assets across LEO, MEO, and GEO. The inaugural mission profile for early 2026 confirms this strategic intent. It will be performing Space Domain Awareness, or SDA, missions.
What does that mean in practical terms for, say, the U.S. Space Force? What is an SDA mission?
It means the Blue Ring platform is carrying highly sophisticated optical payloads like the Caracal and Owl sensors to track and characterize other objects, particularly those operating in the highly strategic, high-value geostationary orbit.
Okay, so they're not just delivering cargo to orbit anymore.
No, they're positioning themselves to manage and secure the orbital environment itself. When you talk about the potential for orbital conflict or espionage, knowing exactly what every satellite is doing and who owns it is paramount. This moves the company into a much higher margin strategic business than being a pure launch provider.
Speaking of challenges, we have to talk about Amazon's massive satellite project, Project Kuiper. It has now been officially rebranded to Amazon LEO. To me, that sounds like a very clear, very decisive signal of a huge shift from the R&D phase to the consumer acquisition phase.
The rebranding is a marketing masterstroke. Kuiper was, an academic nod to a specific built of objects, but LEO is instantly accessible.
It's just low Earth orbit.
It directly references the low Earth orbit domain. It's a simplifying move that tells average consumers, this is internet access. This shift signals that Amazon is preparing for market entry in earnest. And that means managing a logistics effort that is almost military in scale.
And the logistical requirements to support that market entry are they're colossal. Amazon has to meet a massive Federal Communications Commission license requirement,
Huge one.
deploying 50% of their 3,236 satellites by July 2026. That is an insane mandate, especially without their own fully operational heavy-lift rocket like SpaceX's Falcon 9.
The required cadence is staggering, and our research team noted the infrastructure moves designed to meet it. Amazon recently finalized the purchase of 45 acres of land in Titusville, Florida, for over $6 million.
45 acres.
And this site is widely expected to serve as a massive logistics buffer.
A logistics buffer for space assets. Why do they need a 45-acre waiting room?
Because they've purchased launch capacity on ULA's Vulcan and Blue Origin's New Glenn. But the scheduling is tight and the demand is relentless. They need a place to assemble, test, and integrate hundreds of finished satellites, ready for rapid stacking onto their contracted rockets as they come online.
So you visualize it as a massive high-tech distribution center.
Exactly.
But instead of shipping out TVs, they are shipping out internet infrastructure on a launch every few weeks.
That's it. Amazon is preparing for a launch cadence that must rival SpaceX's, but they're relying heavily on third-party heavy lift.
And if that reliance on non-SpaceX lift capacity is the key bottleneck, we should acknowledge the international players who are capitalizing on that overflowing Western launch manifest.
Definitely.
India, specifically ISRO, scored a major validation this week.
They did, and it's a critical success for global space logistics diversification. ISRO successfully launched the heavy commercial Bluebird Block 2 satellite on their LVM-3 rocket.
That's a big payload.
It is. By successfully carrying a 6,000-plus kilogram payload, a genuinely heavy commercial satellite for a foreign customer, they demonstrated the LVM-3's viability as a reliable, non-Western heavy-lift alternative.
Why does the world need a non-Western heavy-lift alternative? Isn't the market saturated?
The heavy-lift market is saturated in terms of demand, but not availability outside of the two dominant players.
Oh.
Global customers, especially those from non-aligned nations or those seeking supply chain resilience, are desperate to diversify their launch portfolio. The LVM-3 validation means ISRO can capture overflow from the congested American and European markets. It establishes India not just as a national space power, but as a crucial, commercially viable global logistics provider.
This incredible operational scale and strategic realignment, it leads us right into our next segment. Okay, let's unpack this. The commercial sector is booming, the logistics are in place, but let's talk about the how.
The engineering.
The incredible boundary-pushing engineering that is making this massive scale and connectivity possible today.
The engineering breakthroughs this week were truly transformative because they move beyond just basic capability and proved industrial reliability. We are moving beyond proof of concept for three major areas:
Which are?
connectivity, autonomous orbital operations, and in-space manufacturing.
The pace is just relentless.
It is. The standout achievement in connectivity has to be the validation of the AST Space Mobile Bluebird Block 2 satellite. This is the hardware that transforms the promise of direct satellite to standard phone service into a technological reality that can scale globally.
The idea of connecting a standard smartphone directly to a satellite 500 kilometers above you, it still sounds like science fiction. What is the fundamental physics challenge that AST Space Mobile has to overcome to make this work reliably?
It is a formidable physics problem, known as closing the link budget. A standard smartphone has two major limitations when communicating with an object in orbit.
Okay.
First, its antenna is tiny, omnidirectional, and has very low gain. Second, it's limited to transmitting in the milliwatt range because of battery and safety regulations. That signal is incredibly weak, and by the time it reaches orbit, it's essentially a whisper.
So if the phone can't shout louder, and legally it can't, the satellite has to have massive sensitive ears to compensate for that whisper.
Precisely. The engineering insight here is that when you remove the ground dish requirements, you simply move the massive infrastructure to orbit. Size is the only reliable solution to the physics problem.
So what did they do?
The Bluebird Block 2 satellite addresses this by deploying a colossal phased array antenna. Our research team notes this array spans approximately 2,400 square feet.
2,400 square feet.
Which is 223 square meters, 3.5 times larger than its predecessors. This sheer aperture size compensates for the phone's deficiencies, providing the gain magnitude needed for high-fidelity link stability.
That is essentially an unfolding communications infrastructure, larger than a standard tennis court, but made of sensitive, high-precision communications equipment. So what was the result of deploying and testing this colossal antenna?
The validation was crucial. The system achieved high bandwidth services, enabling peak data transmission speeds of up to 120 megabits.
120 megabits per second.
Right. This is the difference between an emergency SMS text message and mainstream broadband service. It enables streaming video, high-definition voice calls, and substantial data transfer. It proves the core engineering thesis. If you want high-capacity direct-to-device, you need massive, unfolding structures to manage that physics problem. This technology is actively rewriting the definition of what is possible in LEO telecommunications for underserved populations globally.
That is truly game-changing connectivity. So moving from big ears in the sky to precision teamwork, autonomous systems also went fully operational this week with two major breakthroughs.
Yes, and they highlight the transition to complex orbital construction. Starting with the European Space Agency, their Proba 3 mission demonstrated incredibly demanding precision formation flying.
A subtle but profound capability.
Very. It unlocks new types of orbital science.
What exactly did Proba 3 achieve, and why is this formation flying so difficult?
The mission involves two spacecraft maintaining a separation distance of 150 meters with millimeter-level accuracy.
Millimeter level.
They aren't tethered. They are flying in lockstep, using laser metrology and vision-based sensors to coordinate their movements perfectly. The difficulty is overcoming orbital perturbations and maintaining stability without any physical rigidity. The purpose is to create a virtual giant satellite for solar observation.
A virtual giant satellite.
Specifically, an artificial solar eclipse lasting 6 hours per orbit, allowing scientists to see the sun's faint corona more clearly than ever.
So by flying two separate small craft with that level of precision, they created an instrument that physically couldn't be built and launched on a single rocket.
Exactly.
That is an incredible leap in orbital infrastructure construction. It means size is no longer limited by the fairing dimensions.
It proves that complex distributed orbital architecture is rapidly moving toward operational reality. Similarly, India's ISRO achieved a major autonomy milestone with its SpaceX mission, which focused on orbital mechanics and proximity operations.
This was the docking mission, right, using their indigenous technology.
Yes. They successfully connected two 220-kilogram satellites using the Partia docking system, or BDS. While docking itself isn't entirely new, the critical detail here is the precision of the final approach velocity.
What was it?
The system achieved a gently approach velocity of just 10 millimeters per second.
10 millimeters per second, so about the speed of a snail.
Pretty much.
Why is that so important? Does it really matter if they approach at 1 centimeter per second or 5?
It matters immensely, especially for future, more delicate infrastructure. It demonstrates the ability to execute soft, gentle docking maneuvers without causing undue stress or shock. If you approach too fast, you risk collision, damage, or creating unnecessary forces on delicate structures.
Like fuel lines or solar panels.
Exactly, or the flimsy connections of future lunar habitats. This gentle approach capability is foundational for complex future missions, like assembling those lunar bases and, more immediately, on-orbit refueling and servicing something that demands flawless rendezvous and proximity operations.
And all that in-space precision is enabling new industrial processes that promise to bring manufacturing jobs, ironically, off-world. We've talked about the promise of space manufacturing for years, but this week, it looks like it reached a commercial inflection point with the Forge Star 1 announcement.
Space Forge announced the successful generation of plasma for free-flying semiconductor production. This is huge because it's the first time this high-value manufacturing step has been achieved outside the constrained environment of a space station. They prove they can run a clean, independent factory in orbit.
That's a huge validation for the entire concept of microgravity manufacturing. But for our listeners, why exactly does manufacturing in microgravity give you a better product than manufacturing here on Earth?
The key reason, as highlighted by our research team, is the elimination of convection-induced defects.
Convection-induced defects.
Think of it like trying to make a perfectly uniform crystal or glass. On Earth, temperature gradients cause material to move and mix. That's convection creating imperfections, like tiny bubbles or flaws in crystal structures. In microgravity, where gravity is negligible, you eliminate that movement. You get a much cleaner, more uniform crystal formation.
So if you are building something incredibly sensitive, like a semiconductor or an optical component, you can produce a much higher quality product in space than you ever could here.
Exactly. This is particularly vital for advanced materials like gallium nitride, silicon carbide, and diamond used in high-efficiency electronics for next-generation defense, telecommunications, and high-power applications. This validates a pathway to producing advanced semiconductors that are simply not feasible to manufacture on Earth. The theoretical advantage is now becoming a commercially viable reality.
To make this high-value distributed economy sustainable, though, requires standardization. If we're going to have space tugs and orbiting factories, the basic infrastructure required for servicing satellites, like refueling, it needs universal components.
Which brings us to OrbitFab's RAFTI port.
Exactly.
OrbitFab is aiming to be the gas station in space. And the RAFTI, or Rapidly Attachable Fluid Transfer Interface, is their universal fuel nozzle. The challenge of orbital logistics is immense. If you don't standardize the interfaces, if every satellite needs its own custom-built solution, refueling becomes prohibitively complex and uneconomical.
The analogy of a terrestrial fuel pump is perfect. Every car has a standardized fuel port, regardless of who manufactured the gasoline, the car, or the pump. You just need a universal standard.
And critically, OrbitFab secured major buy-in this week from Europe. They received funding from the European Space Agency to lead the Astral refueling demonstration.
That's a big deal.
This ESA funding is essential because it incentivizes European manufacturers to integrate the RAFTI port into their satellite designs now. This is the critical economic shift, moving from building disposable assets that cost millions to replace to building assets that are refuelable by design.
Which is the foundational economic unlock for the entire in-orbit servicing sector.
It completely shifts the risk model, making satellites infrastructure instead of one-time hardware.
Before we move on to the pure science of the cosmos, let's just take a quick moment to acknowledge those of you listening and watching. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button to help us reach more viewers.
Yeah, and of course, be sure to turn on notifications so you never miss an update on the future.
It's amazing to see all this industrial expansion, manufacturing, and standardized logistics taking hold. But the infrastructure we're building is also enabling scientific discovery at an unprecedented rate, allowing us to gaze outward further than ever before.
Let's shift gears to science, discovery, and the cosmos.
What's fascinating here is that the same industrial and logistical engine we just discussed is also necessary to keep our biggest science instruments running. And those instruments are turning their eyes toward the deepest past of the universe.
And the James Webb Space Telescope, JWST, it continues to rewrite cosmology, and this week brought confirmation of a tremendous breakthrough.
What was it?
Confirmation of the most distant supernova ever observed. Our research team highlighted that this event occurred when the universe was less than 1 billion years old. That is incredibly early in cosmic history, essentially peering back to the very first light.
Just after the cosmic dawn. So the light from that explosion took over 13 billion years to reach us. What were the specific mechanics of this observation?
Well, the event was initially flagged by a gamma-ray burst, which is essentially a cosmic lighthouse of extremely high energy emission. JWST locked on to the fading afterglow of that explosion and performed a spectroscopic analysis.
Okay.
The technical significance lies in the fact that the spectral characteristics of this primordial explosion were surprisingly similar to supernovae we observe in the local modern universe.
Why is that similarity so shocking to cosmologists? I mean, if a star explodes, shouldn't it always look like a star exploding?
Not necessarily for the earliest stars. Standard models of the early universe suggested that the very first stars, known as population 3 stars, would have been metal-poor.
Mostly hydrogen and helium.
Exactly. These metal-poor stars were theorized to have died via mechanisms distinct from modern stars, potentially collapsing directly into black holes without the kind of luminous, iron-rich, standard supernova signature we saw here.
So the detection of a standard core collapse supernova means the universe had already synthesized and dispersed heavy elements, what astronomers call metals, at a much earlier epoch than previously thought.
Exactly. This discovery fundamentally challenges those standard cosmological models. It suggests that the mechanisms driving stellar core collapse and the subsequent chemical enrichment of the cosmos with heavy elements like oxygen and carbon were established much earlier than we thought. The universe matured chemically, faster.
Which would necessitate a significant recalibration of galaxy formation models.
It does. It means the building blocks for complex stars and planets were available sooner.
And speaking of mapping cosmic history and hidden structures, NASA's SphereX mission also released its first complete infrared all-sky map this week. This is less about deep space distance and more about comprehensive data collection, right?
It is a major instrumentation milestone because it's a wide-field observatory covering the entire sky, not just specific targets. SphereX captured the entire celestial sphere at 102 distinct infrared wavelengths.
102.
Imagine painting the entire night sky in 102 different colors that our human eyes can't see. It's a true data feast.
That must create an unbelievable amount of raw data. What is the practical scientific value of having an all-sky survey in that level of detail, specifically in the infrared band?
Infrared light is crucial because it penetrates the massive dust clouds that obscure visible light. On Earth, we can't see the galactic center clearly because of this dust. So this multispectral map enables entirely new studies of cosmology and galaxy evolution by revealing hidden structures.
Star formation regions, early galaxies?
All of it. Cosmic structures previously obscured by our galaxy's own dust. Our analysis suggests this map will be vital for understanding the distribution of matter and potentially mapping the effects of dark energy across the entire observable universe. It helps us see the universe that was literally invisible until now.
We also got deep insights into the current universe from the other end of the electromagnetic spectrum, with the Chandra X-ray Observatory providing a highly technical look into galactic feedback.
Yes, specifically in a region known as the Champagne Cluster.
The Champagne Cluster.
Chandra released composite imaging of this cluster, which is a massive collection of galaxies, where X-ray data shows gas heated to millions of degrees, interspersed with colossal shock waves and carved-out cavities. These are not quiet, peaceful systems.
Let's focus on those cavities or bubbles. What are those physically, and why are they so energetic?
They are regions carved out by relativistic jets of highly energized plasma, fired by the central supermassive black hole. The black hole acts as an immense energy engine, pushing hot gas aside and generating those shock waves. This interplay between the black hole's jets and the surrounding hot gas is known as the feedback loop.
And why is that feedback loop so fundamentally important to the universe? It sounds like a destructive force.
It's destructive, but it's regulatory. It's essentially the universe hitting the brakes on galaxy growth.
How so?
If the central black hole didn't constantly heat and stir the gas would cool too quickly and collapse into stars at a runaway rate. That would lead to hypermassive galaxies that burn out quickly, contrary to what we observe. This mechanism is the primary regulator of star formation in massive galaxies.
So the black hole acts like a giant thermostat, regulating the temperature of the cosmic gas oven to prevent the galaxy from using up all its star-forming fuel too fast.
That's a perfect analogy. The images help astronomers accurately measure the incredible energy output required to prevent galaxies from becoming far more massive than what we observe today. It's a mechanism of universal self-control.
The sheer ambition of both the science and the industrial capacity we've discussed is inspiring. But this rapid expansion is creating undeniable friction and risk, which we have to address head-on. Let's move to the dark side of progress: sustainability and geopolitical friction.
This is the critical tension point of our entire analysis for Tomorrow Unveiled. The faster the industry scales, the greater the environmental and security risks become. The fragility of the low Earth orbit environment was starkly highlighted by the Starlink fragmentation event in late December.
Right. Starlink satellite 35956 experienced a significant anomaly, and the debris and policy fallout dominated the discussions through the end of the year. Our research team characterized it as an internal energetic event,
Likely a tank rupture or a battery failure.
resulting in a cloud of trackable debris.
What's crucial here, and perhaps the saving grace of the incident, is the engineered mitigation. The failure occurred at a lower altitude of approximately 418 kilometers. This is substantially lower than the final operational altitude of 550 kilometers.
Oh, okay.
And this confirms the validity of SpaceX's low insertion strategy.
Which means physics atmospheric drag helps clean up the mess naturally without any intervention.
Exactly. At that lower altitude, the atmospheric drag is high enough that the debris will naturally decay and burn up within a few weeks, avoiding long-term pollution. However, the event prompted a major operational change that highlights the trade-offs inherent in space safety.
What was that operational change?
SpaceX announced that starting in 2026, they would lower all future Starlink operational shells to around 480 kilometers. This significantly increases passive safety-failed satellites decay much faster, but it imposes an enormous operational penalty.
Which is?
Higher atmospheric drag means the satellites must expend more propellant for station keeping.
So shorter satellite lifespans, which necessitates an even higher launch cadence to replenish the constellation. This is a classic space sustainability dilemma.
It is. The solution to safety drives even greater orbital traffic density and propellant use. You solve one problem by accelerating another.
And that dilemma is compounded by rising geopolitical friction in orbit. The dual launch of China's Shenzhou-29 satellites closed out the year, bringing the inspector dilemma into sharp focus. China stated these satellites were explicitly for technology verification for space target detection. Our sources confirm this means they are capable of rendezvous and proximity operations, RPO.
The ability to approach, inspect, and potentially interact with other satellites.
And that creates a major gray zone risk in terms of security.
It does, because in the absence of established, transparent rules of the road in orbit, the intent of an approaching satellite is impossible to verify. Is it approaching to inspect a failed debris asset, which is benign, to gather intelligence, which is espionage, or to physically grapple and disable, which is an overt attack?
And the inability to verify intent forces the targeted nation, say the US or Europe, to assume the worst, leading to necessary but expensive evasive maneuvers.
Exactly. And if a Chinese asset maneuvers toward a U.S. asset and the U.S. satellite expends precious fuel to evade, that expenditure shortens the U.S. satellite's life by days, months, or even years. This could be interpreted as a non-kinetic attack.
A gray zone escalation that uses fuel as the weapon.
Precisely. The lack of direct, real-time communication channels between major space powers to deconflict these maneuvers remains a critical vulnerability in global security. It fuels mistrust and forces expensive defensive maneuvers.
And finally, these complex technical and geopolitical challenges are facing stiff headwinds from terrestrial bureaucracy and politics. The rapid industrial expansion is slamming directly into regulatory speed limits.
The FAA is facing a very challenging situation. The surge in launch activity, SpaceX alone launched 165 times, has consumed an enormous amount of regulatory resource. The FAA is struggling to process the flood of launch licenses and environmental reviews.
So the bureaucracy can't keep up.
We found that if regulatory processes don't streamline rapidly, the FAA itself threatens to become the limiting factor for expansion, stifling the growth we're seeing. It's not just a funding problem, it's an archaic process problem.
Meanwhile, the U.S. federal budget is also in deep limbo. NASA and NOAA face peril due to a looming appropriation standoff, with the continuing resolution expiring near the end of January 2026. This is the definition of a terrestrial headwind impacting space operations.
Budget freezes and legislative gridlock fundamentally hinder new program starts and long-term planning, particularly for critical Earth science missions, which often have lower public visibility than Mars or the Moon.
Right.
We found specific concerns about the political controversy surrounding the potential dismantling or severe defunding of the National Center for Atmospheric Research, or NCLR. That signals a profound political threat to critical Earth observation data.
And symbolically, NASA's The Earth Observer publication released its final issue on December 31st, 2025, ending a 37-year run. The loss of that institutional voice and public communication channel, it weakens the scientific community's ability to advocate for these essential climate monitoring missions at a critical time.
Which raises an important question. How do we secure the future of this complex industrial and scientific endeavor when the foundations on Earth, the political will, the regulatory bodies, and the necessary funding for basic science are so shaky?
It's a question we need to solve quickly before industrial scale outstrips our ability to manage the consequences. And before we explore the final outlook, if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled.
It truly helps us reach new listeners.
So to summarize, the final week of 2025 solidified the shift. We are now fully in the execution phase.
Absolutely. The focus is no longer on if the technology works, but how quickly it can scale and when it will generate revenue.
So we move from the hype of 2025's record numbers to the realization of heavy lift in 2026. This means the debut of Blue Origin's New Glenn to clear the Amazon Leo backlog and the transition of SpaceX Starship Block 3 from experimental flights to operational payload trials.
Including that critical on-orbit propellant transfer demonstration required for deep space exploration. The goal now is profitable functionality.
So what's the big picture for 2026?
The space industry now faces a dual imperative that will define its success in 2026 and beyond. First is technical scalability. proving the economic feasibility of operational concepts like in-orbit refueling, standardized utility ports like RFTI, and routine heavy lift reuse.
And the second imperative?
The second, and far more challenging, is environmental responsibility. Implementing binding, enforceable regulations like the EU and ESA push for zero-degree charters to sustain LEO as a usable environment for everyone, forever.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the escalating launch competition. Specifically, if you think the FAA can keep pace with the industrial scale, and what the real solution is for the challenge of orbital debris.
What's fascinating here is the stark contrast and coexistence.
Yeah.
The technology to see the universe's most distant, oldest stars, the light from less than 1 billion years after the Big Bang, is now operational, existing alongside the complex competitive infrastructure required to send a text message from orbit to a phone in rural Africa. The expansion of humanity beyond Earth is no longer a dream of science fiction, but a daily industrial reality that demands global cooperation to manage the immense risks we are creating at the junction of science, commerce, and national security.
Thank you for diving deep with Tomorrow Unveiled. We'll see you next week.